Yeah, just to answer that question, the system is live right now. Anyone, hopefully live. I was having trouble with the network here, but telepathwords.research.microsoft.com. You can just play with it. I highly recommend test it out, type some profanity in to see how it handles the situation that profanity is something that's common in passwords, but something that websites really don't want you want to be giving advice about. So yeah, go ahead and try the system. I'm going to be talking about something that you can do if you want to go beyond what telepathwords does. So telepathwords can weed out a large number of weak passwords, but there's no way to guarantee that a password is strong. You can never have a user-chosen password that you know is strong. So what I'm going to be talking about is joint work with Joe Bonneau, and it's about storing 56-bit quality keys, so large secrets in the human brain. Now, Joseph Bonneau will not be giving today's presentation for a very good reason. Paper beats rock. Rather, I will be giving today's talk. Now, I usually go by my maiden name, but since I know it's getting close to dinner time and people like to slip out, I will actually be going by my married name, Mr. Jae-Eun Jung. That is the husband of next year's program chair. So just keep that in mind if any of you were thinking of slipping out the back door. So I'll be helping you cruise through the human brain looking for places to store those 56-bit keys. Let's get started. So as I said, user-chosen keys can never be provably strong because there may be something the attacker knows about the user that we don't, something predictable. And so there's no way you can ever prove that something chosen by the user is strong. If you want something truly provably strong, it has to be something that's randomly generated by the system. So when would you want something that's really strong, like a 56-bit key? Well, maybe your master password for that password manager that stores all your other credentials. Maybe if you're sending leaks back and forth or working with a publication and you're worried about government surveillance. That's the logo of Minilock, which is a system for encrypting attachments. So encrypting file systems, encrypting attachments. Or maybe you're a company that has 100,000 employees and you know you can filter out the weak passwords from 99,998 of them, but there might be 2 weak passwords you just can't recognize that an attacker would, that would be able to let someone get a beachhead into your organization. And so you really want to make sure everyone's using a password that's much stronger than 1 in a million guesses to crack. So in these situations, and you definitely, for those of you who appreciated Cormac's presentation, we do not want every website to make people remember 56-bit keys, but for these applications, it might be really important. For basically, when you're putting all of your eggs in one basket and you're guarding that basket, a 56-bit key might be just what you need. Now, it's generally believed that humans, at least by computer scientists, that humans cannot recall 56-bit keys or crypto quality keys. This is the famous comment from Charlie Kaufman in the book with Perlman and Spessner that says that humans are terrible for this. And why is it that computer scientists believe that this is impossible? Well, we have certain models and certain metaphors that we use to think about storage systems. And so first of all, we start with these familiar metaphors. And the problem is we have them, and then we explain our problems using them. So we think about what we would want to do with the human mind, and well, we'd want to be able to write to it, right? We want to be able to store that password. And we want to know that after some period, we can read from it. And we're not quite sure that anything should happen in between. That doesn't happen in a storage system, so we don't really worry about that space in between. And now, we do recognize that writing to brains is different than writing to disks, right? It requires a lot more power, and it requires a lot more time. So it's a lot like etching in stone. And I apologize for the people in the back who chose to sit in the back and can't see the small comments. I did choose Creative Commons images, but I'm a little worried that I may still be the subject of a trademark lawsuit for choosing this one. So computer scientist model of writing, okay, it's really hard, lots of power, lots of time. Just make the user, if the user's really motivated, they should be able to do this. And if you can't give them enough motivation, if they can't do it even if with enough power and time. Clearly, they just can't do it. Well, as a result, our proposed solutions are constrained by these metaphors. And so when things fail, right, we're just back to this, well, we needed more power or we needed more time. And when that fails, we just give up. Well, time, power, annoyance, this does not equal memorization. And if you look at the studies of human memory, this is not how you get to memorization. And the problem generally is your brain is designed to forget random data if it's only been shown it once. Otherwise, you'd have loads of random data in your head that you couldn't do anything to get out and clean out and remember the things that actually matter to you. So really, the problem is time plus power plus annoyance doesn't equal memorization, at least in a single session. If you can get rid of this single session requirement, if you can stop ignoring the space between the write and the read, you might actually make some progress. And that's what we're going to do. This is what we think is a better model, a better metaphor for what should be going on in the human brain. Here we see water and waves have crashed over rocks, not just once in one big one big burst of effort, but over a period of repetition, every 12 hours, and they've etched in this incredible quantity of entropy. This is really handy. And of course, this is similar to what we actually do when we're studying, when we want to actually learn something. Now, most of you have gotten degrees. You didn't do it without some form of studying, except maybe Dave. But for those of us who aren't that bright, we went and we got those cards, and we used the flashcards, and we used repetition, and we used repetition over time. And through spaced repetition, we were able to learn those mostly unimportant things that we needed to do to get through the educational process. And so we know this works, right? Medical students do this, students do this. This system works for learning. If we could only apply spaced repetitions to passwords, then we could probably get people to learn 56-bit keys, or at least that's what we hypothesized. And so when you look at how this would work, you have to remember that when your memory is kind of like DRAM, right? If you write it enough and if you read it, reads are like writes, just like in DRAM. Every time you have to remember something, you're doing something that's going to help you remember it again in the future. And so if you have a repeated number of these rehearsals, when the time finally comes to read, you're going to have a success. So how do we apply that to remembering secrets? Well, we built a system, and this is how it worked. So you'd sign up, just like you sign up for any service. You create a name. We let you create a password. This was just going to be for the temporary purpose until you learned the 56 bits. And then when you went to log in, you'd type your password. Once we'd verified it, a security code would appear. In this case, it was 2 words, and you would then be asked to copy those 2 words. And in other cases, so some participants, when we ran a study, would get words, sets of words, and these participants would get sets of letters. This is 4 letters. When we chose words, they were from a set of 676 words, which not coincidentally is 26 squared, so that 2 letters were always equal to 1 word when we did the study, same amount of entropy for 2 different conditions. So here we have 4 letters, and when it appears, people just copy it. So the way we trained them is we never actually told them to memorize it. We never asked them to do any effort other than copying it down. It's just that each time they logged in, it took a little longer before we showed them what we wanted them to copy. So that one took it took a third of a second more for every login. So after a while, it starts to get annoying to wait. But you wait and then you type it in. And we told them, well, you don't have to wait. If you know it already, you can just type it in. And after about 10 logins, we hoped they would. So once they learned the first one, we'd give them the second one. Once we gave them the second one, they learned the second one, we gave them a third one. You get to 12 lowercase letters, that's 56 bits. Similarly, 6 words, 56 bits. So does this work? To test it, we created a human intelligence task on Amazon Mechanical Turk. Now, we didn't want to tell people to memorize the password because we really wanted participants to be putting no effort into learning this. We wanted to show that people could do this without trying. So we told them that we were doing a study about this attention task right here. And the way this attention task worked is you were given 60 seconds. If you saw the word left, you were supposed to type a key on the left side of the keyboard. If you saw the word right, you were supposed to type a key on the right side of the keyboard. So this was presented as a psychology test. And it's very similar, in fact, to the Stroop effect, or if any of you are familiar with the Stroop effect, where you're supposed to report on colors when there's the word that is a color and then that word is written in a given color. So very similar. It looked just like a psychology experiment. And we wanted people to be logging in about the same number of times a day they would if they were typing in their enterprise credentials. So every time they, say, came back from the bathroom, if you're working for a company where you have to lock your screen when you leave your office, you're going to be logging in about 10 times a day. We figured we wanted them doing it no closer than every 30 minutes. So we didn't want them logging in a period of less than 30 minutes. So we created these rules for the study. We offered people $19. They needed to do this attention task 90 times, and they couldn't do it twice within 30 minutes. They had to wait 30 minutes before doing it. Now, what we didn't tell them, they were going to have to log in each time. And what we didn't tell them was there was this additional code they were going to be learning during the login process. And so that's how the process worked. They had 15 days, and generally they finished in about 8 or 9 days. So they signed up for the study, we got their user-chosen password, and then we assigned them a 56-bit key, encoded it either into letters and words, and away they went. And when they signed up, and every time they did this attention task to keep up with this cover story, we asked them how long it had been since they'd slept and whether they'd consumed any caffeine. This maintained the cover story that we were really studying attention. We'd give them this test, and after we'd give them the test, this 30-minute timer would count down until they could do it again. And if they tried to log in before, they'd just get the timer updated with whatever time was left. And then when they'd go and type in their password, they'd be typing in the code. After the password, they'd have that code, and we had a little message that told them what the code was for, and it was because we were having problems with people. We needed additional security because of gratuities. And so that's how the study worked. We had 223 people sign up for it. We had a control group. Those people didn't have to learn a code at all. We had assigned people to the control group with probability 20%, to the letters and words group, each with probability 40%. And the reason for that is the control people, all we were really getting from them is to find out whether they would be dropping out of the study less than people who had to do this additional work. And in fact, 85% of the people completed in the control, whereas only 73 and 75 did in the other two groups. This was not statistically significant, but there's good reason to believe people were dropping out if they had to do the extra work, because if you look at when they dropped out, people found out that they had this additional code on their second, when they played their second game. The first one they played right after they signed up. The second one, it was the second one where they then were assigned the code. So quitting after 2 games or 3 games, no one did it in the control, but 9 out of 92 did it in the letters group. That's 10%, and 12 out of 90 did it in the words group. So this is extra work. Almost everyone received their full security code out of 133 people. Only 6 did not. 2 of them may have actually had legitimate memory problems, but 4, very interestingly, dropped out, stopped learning. They learned the first code, but not the second code. So they only got the first 4 letters or 2 words. And once they memorized them, they stopped being able to memorize anything. And this we found very curious. There was a possible explanation for it. When we gave them the first code to memorize, we didn't tell them that they were memorizing anything, and if they memorized, they didn't know there would be any harm if they memorized it and showed that they'd memorized it, so they started typing it in before the code appeared. When we gave them the third one, we could say, hey, we're done. You're not going to get any more. We couldn't say that for the second one, right? They had just learned something. We gave them more work to do, and then they were starting to figure out that in fact, if they memorized this one, they might be given more work to do. And in fact, when we asked them we emailed them to ask them what had happened, and we got some very entertaining responses, basically saying, what do you think, we're stupid? Of course, we didn't want to show that we had learned the second code. As one of my favorite, not so literate or eloquently literate participants said, if there are people who fell for that, please do not tell me, as I would be very disappointed and fearful for the future of humanity, LOL. And the LOL was important. So here's a graph of how quickly people memorize their codes. Remember, they didn't see the third code until they'd memorized the second one and entered it 3 times without seeing it. And same, they didn't see the second one until they'd memorized the first one. And what we see is that by 40 login attempts, most people have memorized just about everything. Now, you may, by the way, be worried that people are going to forget, or that people are going to have a hard time memorizing the third one after they've learned the second, and the second one after they've learned the first, that there's some limit of memory. It gets harder as you do more. But in fact, they took the most time to learn the first one because they didn't quite understand necessarily. Some of them might not have understood the concept that they could type things in sooner and they didn't have to wait for that stuff to copy. By the second and third one, they were actually learning quicker. So 3 days after participants completed the study, we followed up with an email, and we said, hey, come back, and we gave them one chance, without any hints or help, to type the code again. And of those who, just about everyone came back. In fact, the numbers were higher than this, but some people came back a little late, and so we had to disqualify them. They had from day 3 to day 7 to come back. 82% in the words group and 93% in the 82% in the letters group and 93% in the words group still were able to recall. That looks like a big difference. It really is a big difference. It's 7% of people forgot in the words group, and 18%, more than twice as many, forgot in the letters group. But because of these sample sizes, the difference is not statistically significant. And by the way, we did check to see whether they were writing these down. They generally weren't, but even if they were writing it, these numbers weren't affected by people writing it down. The numbers don't get any worse if you throw out the people who were writing information down. So if you recall the numbers that Saranga quickly went through in the last paper on what happened with all of those 6 policies where people got to pick their own passwords and come back in 2 days to 3 days, not 3 to 7 days. In that study, recall rates maxed out at 74%, which means in the best case, basic 8, all you have to do is pick 8 letters of your own. If there was no training, if there was no repetition, 26% of people, at least, in the best case, were forgetting their passwords. Whereas in our study, it was 12%, right? So this is a big improvement. You can memorize 56 bits better with training than you can memorize a password of your choice. In other words, no password memorization is, no user-chosen password is going to be good unless there's some memorization process. This is not user-chosen versus random. There has to be a repetition for you to remember anything, regardless of whether it's user-chosen or random. Okay, there is one caveat. We did follow up again after 2 weeks, and the recall rates really go down. And this is also true in the human memory literature. If you wait for a period longer than you use the data, so if you memorize something or were using information for a period of time X, and then you wait for a period longer than X of idleness before asking for it again, people's recall rates are going to go down. And that's indeed what we saw. Now, that should get better just as people are using these secrets for a longer period of time. But there are also tricks we can play that we're trying in our next study that we think will improve this. So in summary, since I've got this flashy orange thing in front of me, courtesy of David, in summary, I like to sum up with this quote from one of our participants. Remember, these are Turkers. They are a little bit different from a general demographic, but these aren't often technical people, and they're certainly not memory champions. And this one, this is my favorite. It was surprising that you did this follow-up, because I did not expect it. After having to enter the code so many times, the words are branded into my brain. So maybe we did get back to that model where we are indeed able to figure out where that right head should go. And this matters because there are some passwords that really matter. And if you add up the total time, remember, people weren't actively trying to memorize, but just the time they were copying that stuff down, the extra time we added to those 90 logins was about 5 to 10 minutes. And remember, they really only needed the first 45 to do the memorization. We could have thrown out their passwords after that. So thank you very much. I also have some acknowledgments from folks from Cambridge, IBM, CMU, Microsoft Research, and Princeton who helped us out, as well as the somewhat anonymous reviewers, including the one who word wraps to very short lines. Not going to name names. Thank you.
for one question.
Thank you for a nice presentation, Andrei Kusin from Eurocom. Do you have some insights, or do you plan research on looking how multiple secrets affect the memory and recall rates, and storing each group on which side, and like the
interference? Yeah, this is generally referred to as interference. It is an important problem. It should be less important for this because we really don't want you to have to memorize more than 2 or 3 of these. We can imagine 3 scenarios in the paper where you would need to do this. Hopefully you can keep it to 2 or 1. We did look for interference in that we were looking to see whether people had a harder time remembering their last 2 words after they had had previous 4 words, or if they had a hard time remembering those last 4 letters after the first sets of 4 letters, and they did not. At some point, you would reach interference, but we didn't see it. It's certainly something you could study, but we did not reach that point yet.
Thank you again.
Thank you. Class dismissed.